Hello and welcome to this clip introducing us to benzene. It'll cover the structure of benzene and how we draw it, a look at the Kekulé model and its limitations, and a quick guide to naming arenes, or aromatic compounds with benzene rings in them. So before we go any further, it might be worth just spending a little time just reviewing what an aromatic compound is and how it fits in with the rest of organic chemistry. So if we imagine within the circle are all organic compounds, so these are all the carbon-based compounds that fall under organic chemistry, so including hydrocarbons, including carboxylic acids, ketones, etc., the things that you've come across in your first year. Within that category are what we call aliphatic compounds. So within that category you have something called alicyclic compounds. So aliphatic compounds are all non-aromatic organic compounds. Alicyclic compounds are aliphatic compounds that also happen to have the carbons in a ring of some description, but they're not containing a benzene ring. And in another category you get aromatic compounds. These all contain a benzene ring. So for the purposes of A-level, you really only have to concern yourself with either aliphatic compounds or aromatic compounds. So before we go any further, it's also worth having a look at carbon-carbon double bonds again. So you remember that the carbon-carbon double bond has restricted rotation, and if it's contained within a compound, it'll turn bromine water colourless. And perhaps what's most relevant to this clip is the bonding in carbon-carbon double bonds. So the sigma bond is an orbital overlap between atoms, in this case the carbon atoms, and the pi bond is the sideways overlap between p orbitals. So before we explain what's actually going on in benzene, which is slightly different, we have to delve into its history. So the first person to actually isolate it was actually Michael Faraday. He was actually more famous for his work with physics and electricity, but he was doing some experiments on distilling crude oil and managed to isolate a compound with the molecular formula C6H6. So perhaps one of the most important people to move us forward on benzene was Kekulé, and he came up with a structure for the displayed and skeletal formula that would match what you would think C6H6 would actually be. And he came up with this idea through a dream. He dreamt that snakes were chasing their tails, and in a ring they grabbed onto their tails, and basically that caused him to wake up, and he thought that must be what the structure of benzene actually is. So this particular idea was vastly ahead of its time, but it does have a few potential problems that we're going to talk about in a sec. Okay, so let's have a look at where the double bonds go in Kekulé's structure. If you look at these two versions of the Kekulé structure, you'll see that the placement of the double bonds are actually being shifted slightly around the ring. So if we were to look at how this might take place, using curly arrows, you can see how a movement of a pair of electrons from a double bond onto one of the single bonds can actually shift the position of the double bond around a little bit. So when this happens, it means that essentially the electrons are constantly on the move, because they're going back and forth between these two possible ways of writing the Kekulé structure. So what this actually leads us to is a resonance hybrid. So a resonance hybrid is the term we use to describe when you have the position of a double bond in an organic functional group or organic molecule moving back and forth between two separate locations adjacent to each other. So this gives rise to the classic hexagon with a circle inside it, which we use to represent the benzene ring. So the ring structure, the actual circle inside the hexagon, represents the delocalization of the electrons. So when we draw the skeletal formula of benzene, we draw it like this. And here's the correct way to draw the displayed formula of benzene. So when we actually hydrogenate benzene using hydrogen gas and a nickel catalyst, the enthalpy change is actually a lot less than what we'd expect. If you were to assume that benzene had a 3 carbon-carbon double bonds, each carbon-carbon double bond has a hydrogenation enthalpy of 120 moles per kilojoules per mole. So if you had something with 3 carbon-carbon double bonds, you'd expect it to have a hydrogenation enthalpy of minus 360. So when we actually hydrogenate benzene, you actually get minus 208. So it's actually a lot more stable. And there's other problems with Kekulé structure as well. In 1929, Dr. Kathleen Lonsdale, an English chemist, proved that the carbon-carbon bonds in benzene were the same length all the way around the ring. She did this using a technique called X-ray crystallography, and she used methyl benzene, or benzene with a methyl group coming off of it, as her choice of compound to prove this. Let me try and explain what I mean by this. If you take a carbon-carbon bond, like so, it has a certain length due to the attraction between the nuclei of the carbon atoms and the bonding electrons. A carbon-carbon double bond is shorter because there's more attraction. And what Lonsdale did is to prove that the actual bond length is identical all the way around, not slightly shorter for the carbon-carbon double bonds and slightly longer for the carbon-carbon single bonds. So that's another problem with the idea that Kekulé proposed, where they have carbon-carbon double bonds alternating with carbon-carbon single bonds. If you try and react benzene with bromine water, it doesn't decolorize it. So as you know, the decolorization of bromine water is the standard test for the presence of carbon-carbon double bonds. So if it doesn't decolorize bromine water, they can't be present. So what actually takes place is all the pi orbitals in the carbon atoms overlap sideways and all around the ring, creating what we call a pi system of delocalized electrons. So if you look closely at the diagram, you can see that each carbon has 3 normal covalent bonds, 2 to neighbouring carbons and 1 to a hydrogen. Carbon has 4 electrons in its outer shell, so the 4th valence electron gets involved in the pi system. It becomes delocalized, they can move around, and therefore, because they can move around, they're not fixed in one place, so this means that they're less available. If they're less available, we have what's called lower electron density, and that makes the benzene ring less able to induce a dipole or attract an electrophile to undergo electrophilic addition in the same way that carbon-carbon bonds in alkenes can do. So this makes benzene more stable and less reactive than alkenes. So let's go through a quick guide on how to draw the benzene structure. There's actually 2 possible ways that are acceptable on the exam syllabus to do this. You start off by making sure you draw the atoms and all the bonds. Now you draw in the orbitals. It takes a bit of practice, but try not to cause them to hide each other out. Now you draw a dotted line between the orbitals and the top, around the ring, and the same from the bottom. So that's the top one done. So you need to also make sure that you're labelling this correctly, like that. So you label the p orbital and you label the sideways overlap of the p orbital, so it's clear to the examiner exactly what part of the diagram you mean as the orbitals and exactly what part of the diagram you mean as the sideways overlap between them. Now you're probably taking a little look at this and wondering, can it be cleaned up a little bit? I'm sure it could be drawn a little bit better, but the basics of it are there. But it's something that requires practice to get right, so it's worth going away and trying this a few times to get it nicely arranged, nicely in place, so that the bonds and the atoms and the orbitals and their sideways overlap are all clearly involved in your diagram. Another way of drawing it is like this, where you have 2 donut-shaped rings above and below the ring of carbon atoms. It's really up to you which of the 2 methods you use. Both are acceptable, but they both need to be labelled. And if you actually draw the donut-shaped rings above and below, that's another way of showing the delocalized pi system. So both are ways of showing the delocalized pi system, but in the method at the top, which has the individual orbitals and the dotted lines, that method actually shows the orbitals themselves. So you need to specifically label the orbital and also then the sideways overlap between p orbitals. So briefly on naming aromatic compounds. If you look at these examples, they have two substituents in each case. If, let's say, the methyl group wasn't there, so imagine that it just had the chlorine in the first one and the same in the others. Each case would be chlorobenzene. Let me try and illustrate. So if you now imagine that the CH3s weren't there, you can see I've sort of scrubbed them out slightly. It was just chlorine, it would be called chlorobenzene. If I took the chlorines off and just had methyl groups, I'd be left with something called methylbenzene. What I actually have here is two substituents in each case. So if you look at the one on the left, there's two ways I could count my carbons. I could count them anti-clockwise, starting with the methyl group, and that would make 6 chloromethylbenzene. So instead what I do is I count clockwise. I count so that the chlorine is on carbon number 2. So what I'm doing is I'm making sure that the chlorine is on the smallest possible number. Rather than being on carbon 6, it's on carbon number 2. Hence 2 chloromethylbenzene, 3 chloromethylbenzene, and 4 chloromethylbenzene. So let's have a look at a typical A-level style question on the structure of benzene. There isn't much to read, so we're straight in. Let's have a look at the first sentence. It says cyclohexene, C6H10, reacts with hydrogen to form cyclohexane, C6H12. It says the enthalpy of hydrogenation is 120 kilojoules per mole. So that's a piece of data, isn't it? And like we've always said about data, you keep a note of it for later on. It says suggest the conditions that will be used for this reaction. So looking at the question, cyclohexene is simply a cyclic alkene. It's what's called an alicyclic compound, if you remember the beginning of the clip when we were reviewing the different types of organic compounds. So if it's an alkene, it behaves like any other alkene and undergoes electrophilic addition. In this case, it's adding hydrogen onto the carbon-carbon double bond to make cyclohexane. So for that particular reaction, it's just a question of remembering what happens with alkenes. All that's happened is they've told you about a cyclic alkene. It's no different to a normal alkene, straight chain alkene. It's just a normal carbon-carbon double bond undergoing electrophilic addition. Nickel catalyst and heat are the two conditions. Don't forget that so a catalyst can actually be considered a condition because it doesn't actually react, does it? It remains unchanged at the end of the reaction. It's not just heat, it's also the nickel catalyst. Then it says give the structure of the hypothetical means it's the theoretical species, cyclohexa-1,3,5 triene. So let's think carefully about what that name actually means. It's obviously a ring structure. The hexa part means there's 6 carbons. 1, 3 and 5 will be the positions of the carbon-carbon double bonds. There are 3 carbon-carbon double bonds because it says tri, and ene means that there are carbon-carbon double bonds in the first place. So it's obviously going to be something like this. Seem familiar? It should do, because it's the Kekule structure, isn't it, from this very same clip. Then it says calculate the value you would expect for the enthalpy of hydrogenation of this species. It doesn't say state, doesn't say suggest, it says calculate. Now calculate means that you need to use data. And the data that we've got is the minus 120 kilojoules per mole. So how many carbon-carbon double bonds have you got? You've got 3. So if each one of them is minus 120 kilojoules per mole, it's obviously going to be minus 360 kilojoules per mole for 3 of them. Okay, so now it's time to bring the page up a little bit so we can see the rest of the question. So it says benzene C6H6 has essentially the same formula as cyclohexyl 1,3,5-triene, but its enthalpy of hydrogenation is only minus 208 kilojoules per mole. So we've covered that in this clip as well. It says comment upon the difference between this value and that obtained in part A, III. In other words, our minus 360 kilojoules per mole. So looking back at the question, there's your cyclohexa 1,3,5-triene. It might be helpful at this point, you wouldn't have to put this in, but just to actually draw it out next to that skeletal formula to remind yourself exactly, as in displayed form, what you're looking at. So even though the question doesn't need it, you might find it useful to pop a displayed formula up there so you can see what you're dealing with. So there's 3 things that they want from you. This is a recall section of the question, so it's a question of going back and finding out what those 3 things are. Or obviously, if you're in this situation in an exam, making sure you've thoroughly revised what the 3 things are. So benzene being more thermodynamically stable than expected is a reference to the fact that its enthalpy of hydrogenation is significantly lower than the enthalpy of hydrogenation of the species cyclohexa 1,3,5-triene, or should I say the hypothetical species cyclohexa 1,3,5-triene. So obviously, because in the question it said comment upon the difference between this value and that obtained in A part III, I've made a mathematical reference to the fact that it's not just more stable because its enthalpy of hydrogenation is lower. I've said by how much. So I've said that it's 158 kilojoules per mole lower. So the next thing they want you to do is comment. Comment means say something about it, maybe even give a reason why. So that reason would be the delocalized pi system of electrons in the benzene ring. So moving the question up a little bit. It says the structure of benzene is said to consist of a 6-membered carbon ring with a system of delocalized electrons. Although it's unsaturated, it exhibits different reactions from those of alkenes. So that's interesting, isn't it? It can't be described as saturated, because saturated means the carbons have 4 covalent bonds for each carbon atom. This doesn't have 4 covalent bonds for each carbon atom. So the 2 things to say for delocalize is the electrons are shared between more than 2 atoms in a compound, so they can move around the compound over more than 1 bond. So they're involved in bonding, but there's not just 1 bond that they're held in. There's more than 1 bond they can move between. And in terms of unsaturated, it's best to steer clear in this context of talking about carbon-carbon double bonds for obvious reasons. So you can stick to 1 or more carbon atoms have multiple bonds. That's safe enough to cover you for the benzene ring if you're asked about unsaturation. Then it says, what structure would you expect benzene to have if it showed reactions similar to the alkenes? So it's exactly the same as before, but what they're testing out is whether you fall into the trap of writing out a single carbon-carbon double bond. So it's not an ethene molecule we're talking about, it's what structure would you have benzene, what structure would you expect benzene to have? So because benzene is C6H6, you have to write out something that is C6H6, but also has carbon-carbon double bonds. So even though you may have drawn this structure once already in the answer, they're asking for it in a different context here. So lastly, 3 pieces of evidence for 3 marks that benzene does not have such a structure. So that's what we've gone through in this clip, and if you're doing this video as part of your revision, you'll have to have looked at it in your textbook as well. So this is quite straightforward. So your first point would probably be that the benzene doesn't decolorize to bromine water or undergo other electrophilic addition reactions. Carbon-carbon bond lengths in benzene have been shown to be the same using X-ray crystallography, so they're not different from each other. And then finally, the enthalpy of hydrogenation of benzene is lower than expected, just like we've looked at in this question. Okay, so let's have a quick look at the mark scheme. So this question was just from a general pack of questions. It's of similar standard to the ones that will be on your A level. In the textbook it may not mention platinum catalyst and room temperature, but they definitely have covered nickel catalysts and heat from last year, from your first year, when looking at hydrogenating alkenes. The rest of it is pretty much what we've just talked about. This part here, a 2-electron 2-center bond, all they mean by that is really this: atom A, atom B, like that. So we've had a look at those kind of things before, so that's nothing new. Are dispersed or spread or can move over a greater number of nuclear centres. You can probably work out what that means. The idea that they can move beyond just 2 atoms, they can go over 2 or more atoms. And unsaturated, 1 or more carbon-carbon bonds or multiple bonds. The compound will chemically undergo an addition reaction with hydrogen. So therefore you can add hydrogen onto it over the carbon-carbon double bond. But in this particular case, because we're talking about benzene, there aren't carbon-carbon double bonds present, so it's safe just to leave it as the compound will undergo an addition reaction with hydrogen. I personally would suggest maybe steering clear of that when you're talking about benzene, because the whole point of benzene is it doesn't undergo addition reactions very easily. So I'd stick maybe to just saying 1 or more carbon-carbon bonds or multiple bonds. So my advice would be to maybe stick to this one here. And as you can see, like we said, same structure twice but in different contexts. Benzene doesn't undergo electrophilic addition reactions such as decolorizing bromine water. Let's have a look at the other stuff we've got. I wouldn't worry too much about disubstituted isomers in that case. Electron diffraction, X-ray crystallography, shows that all the carbon-carbon bonds are of equal length or in between carbon-carbon single and carbon-carbon double bonds. And we talked about the enthalpy of hydrogenation of benzene being less exothermic than expected. So those would be the 3 most likely ones they'd expect you to come up with. These are other things that also happen to be true, but you don't necessarily have to have these in your long-term memory. Any 3 of those things would get you 3 marks. Okay, so hopefully you found this a useful introduction / revision to the basics of benzene. And the exam question at the end gives you an idea of how to approach these styles of questions, these more demanding styles of questions that are on the newer spec papers. If you have any queries at all, obviously take it to one of us in the subject extension or contact your teacher. In the meantime, thanks for your time, thanks for listening, and see you soon.